Welcome, everyone. Hello. I'm Heather Downing, and today we're going to explore how modern tools and techniques let us navigate through time series data at very fast speed. We're going to be traveling through time, just like the DeLorean, analyzing the past, monitoring the present, and even predicting the future. And the best part is you don't need a flux capacitor, although I would love one. If you've got a hint on where to get one, let me know. So let's talk a little bit about what we're going to cover today. First, we'll be exploring what time series is actually, and why it's unique. And then we'll see how to analyze historical patterns in our data. Think of that as our 1955, which is why I'm dressed like this today. Next, we'll look at real-time monitoring, or the present, of 1985, using techniques to efficiently write and read data. And finally, we'll jump to 2015 and look at future predictions and trends. Of course, when the movie came out back then, that was the distant future, and now we've surpassed it, but the concepts still hold true. And to bring it all together, I will show you kind of a little dashboard monitoring system, monitoring several DeLoreans at once, and why sometimes that can be a little squirrely to do. Remember, we're not thinking in 3 dimensions here, we're thinking 4th dimensionally. Yes. All right. So what exactly is time series data? How many of you have already played with it? Okay, quite a few of you. All right, well, then you just get to hang out with me anyway for the presentation. Normally, when I see it, it's often done in an observability fashion, which is just time-stamped data, right? It's a sequence of data points collected at regular intervals over time. That's also done quite a bit in the financial industry, in the IoT monitoring, and it's quite important in aerospace, monitoring where different aircraft are at different times and what is running. It's an ordered collection of values where each value is associated with that timestamp so that you can show how a variable evolves over time. And think of server metrics and sensor readings and stock prices or application events, really anything that you can measure. All right. Now let's talk about one of the biggest challenges of time series data, handling what we're calling high cardinality. This is new for me because I never had to deal with time series data all that much before, so I had no idea really what the complexity was about. It's a term that really sounds complicated, but the concept is simple. It just means that each unique tag combination creates a new data point that you have to mess with. For example, imagine you are tracking server metrics, and if you have a tag that's by host name, application, region, and customer ID, you might suddenly have millions of unique time series as you go. Each one requires storage and indexing, which does affect your database performance. That grows into millions of data points, which gets very expensive, and ultimately really hits your queries. Not to mention, visualizing that can be really challenging. It's hard to wrap our brains around some of the way that this data is overlapped. To tackle these time-based challenges, we need the right tools, and for our journey today, I've just picked 3 powerful technologies, which is, of course, .NET for just our application to build a little console app. And I've chosen Influx Data because I work for them now, but it doesn't really matter which of the time series databases you use in order to get this accomplished. And again, because it's just easy to grab them, I'm using Grafana for visualization, but you could build your own dashboard with React or something, or you could use something like Power BI or many of the other real-time dashboarding tools that are out there. And these are a pretty decent stack for figuring out how it all moves together. The purpose behind this talk today is really for people like me, because again, I was fairly new to this last year, and I needed to wrap my head around exactly why I would care when about anything in this stack. All right, let's journey back to 1955, or at least the equivalent in our data lifecycle, which is historical analysis. Looking at historic data poses unique challenges. In the early days of computing, we had magnetic tape and punch cards with extremely limited capacity, although Richard did point out to me that they have good battery life. Data analysis was often done manually because storage was expensive and processing power was limited. Today, we have different challenges, and we can store petabytes of data, but efficiently querying and analyzing is pretty much the big challenge. And that's why specialized time series tools come in. You can technically do this with a relational database. You can do this many different kinds. It's really an approach. But when you deal with a purpose-built solution, it is much easier because they're already used to these kinds of challenges. One of our key takeaways today is learning to read time series data efficiently with SQL. And the tool we're using today for the time series database is Influx, which supports SQL queries, but so does ClickHouse and Prometheus, etc. This makes it accessible if you're already familiar with relational databases like me. When reading historical data, performance considerations are pretty crucial. So here's some optimization techniques you might consider. Using time bucketing or aggregation to reduce data volume. For instance, rather than querying every second of data over a year, just aggregate it into hourly or daily buckets eventually to go through. You can also limit time ranges and where clauses to improve your query speed, and create specific indexes for frequently queried fields to speed up common operations. Trying to avoid the select star to reduce network and processing overhead was the first thing I completely missed when I started, and I really only needed to retrieve the columns that I needed at the time. But I'm so used to select star was just my regular semi-non-changing data that I kind of forgot when it's a plethora of data coming in all the time. You have to be really mindful of that. And then the query example on the right shows these principles in action. We're using time bucket to aggregate by hour, selecting specific fields, filtering by location, and a specific time range, then grouping and ordering our results. These optimizations can turn a query that might take minutes into one that completes very fast, milliseconds. Some of the latest databases themselves with queries can do nanoseconds as well. One of the most valuable aspects of time series analysis is finding patterns in historical data. Just like dance rhythms have patterns, time series data also follows identifiable patterns too. There are several techniques we can use to detect those patterns. Correlation helps us find relationships between different metrics. For example, does CPU usage correlate with memory consumption? That's a good thing to look at. Maybe some trend analysis using moving averages helps us to spot longer-term directions in our data that smooths out the short-term fluctuations you might have. Seasonality identification helps us spot repeating cycles in data, like daily usage patterns or weekend versus weekday difference. And, And by identifying these patterns, we can understand normal behavior versus anomalies, predict future trends, and make better decisions. In our DeLorean analogy, this is kind of like understanding the patterns of time travel to make sure they'll be in the right place at the right time. So as we collect more and more time series data, managing database growth is pretty important. This slide addresses another key takeaway, which is handling scale from thousands to millions of data points. You need to make strategic decisions about data retention. Keep raw data when high precision is needed for regulatory requirements. This is very common, especially in the EU. And aggregate data when you're trying to just analyze long-term trends overall, or when storage costs are pretty expensive. Do you remember when storage was cheap, but now cloud's getting expensive? Not everybody does this on the cloud, and I actually suggest that you don't, but sometimes it's just unavoidable in order to share things with other teams. There are several data access patterns you can do when deciding what you can make more efficient. There's a lot of different options you can do. The first one is downsampling. I'm sure that's probably something most of you are familiar with. Yeah? Cool. It just reduces the resolution of older data. For example, keeping 1 second granularity for the most recent week, 1 minute for the last month, and hourly data beyond that. That's one thing that is done often just to get an idea of the day, wrapping up for the day. Compression is specialized algorithms for time series patterns that reduce storage requirements. Sometimes it's just down to the pointer in the database so that you can then either revive later or bring back up, but oftentimes this is for your longer term cold storage option. And a multi-tier architecture balances that performance and cost. So maybe only keeping recent data in your high-performance storage, your hot storage, is the best way to handle it if you need to respond in a relatively short fashion. The best example of that is when air traffic control needs to respond to data that they're seeing coming in from airplanes in real time. But they won't need to respond that fast the next day. Then that becomes historical, and maybe in order to hold on to it, they might do a regulatory one. But if they just want a dashboard really quickly to look at each day, they might downsample or just pull it out into a different place entirely. Now let's travel to November 5th, 1985, and we're going to pretend that that's today. Our present day analogy for real-time monitoring. This is the part of time series data that got me excited. So when they were trying to harness lightning to power the DeLorean, precise real-time monitoring was pretty essential in order to get that right. And one of the most important things you can do is to be able to read and write things quickly. Line protocol is something that Influx uses that is a little bit faster, and I've got a little bit more of measurements later, that is faster for writing time-stamped data. You can also think about how much closer it is to the source if you could do it on board the actual device or machine that it's on. The best example I have of this is when in the satellite industry, they might need to adjust something like a landing trajectory because it's autonomous. So it needs to be able to analyze things on, like, right on that Raspberry Pi or whatever size that you've got server on the satellite. And this is why it's important to just consider how complex your queries are to write. All right, and the elements of this are pretty simple. It's just a measurement and a field set. You also can do an optional tag set and timestamp. And these are key value pairs for your metadata. All right. So let's dig deeper into what this is. This format makes it efficient, right? That's what I mentioned. And the basic pattern looks like this: comma-separated key value pairs. It's actually smaller compared to your JSON, and it's definitely faster to parse. Here's a good example you got right there. Let's look at the example down there. So the single line contains the measurement name, location, and driver tags for these DeLoreans, the speed and power level fields, and a precise timestamp. If you compare this compact format to the equivalent JSON, it would be much more verbose. And this efficiency becomes really crucial at scale when you're writing millions of data points per second. Every byte and every millisecond counts. While line protocol is already efficient, we can further optimize throughput with batch writing. Instead of sending each data point as a separate HTTP request, batch writing groups multiple points into a single write operation. And then this approach drastically reduces network overhead and improves database write performance. So the .NET code snippet that I've decided to include demonstrates how to implement batch writing, uses an InfluxDB library. And for optimal performance, you'll want to adjust batch size based on your specific network conditions and database capabilities. If you're too small, you're not getting the benefit of the batching, so what's the point? If you get too large, and you might encounter humongous amounts of timeouts. Don't forget robust error handling for failed write operations. I'm sure you're all expert SQL Folks in the audience, but not everybody does that. And you'll need strategies for retrying or logging failures to prevent that data loss. These techniques directly address the second takeaway, which is writing data efficiently and helping to ensure your system can scale really well. To really appreciate why it matters, let's compare it directly to JSON. Look at the comparison on the right side of the slide down at the bottom. The same data point represented in line protocol is about 80 bytes, while the JSON version is around 180, more than twice as large. This size difference directly impacts network transfer times, parsing speed, and storage requirements. So you could actually theoretically get hit at multiple places. Line protocol is also faster to parse and write since it doesn't require that complexity. The efficiency just isn't about saving storage, it translates directly into better performance and the ability to handle higher volumes. You may not even need this. In fact, for a lot of what we're doing today, JSON is totally fine. But it depends on how precise you need for your real-time monitoring. This is really only comes into the present, right? Let's tackle one of the most important challenges in time series data, high cardinality. Remember, high cardinality means you have many combinations that are unique of tags that create separate time series. First, be strategic about your tag selection. Keep high cardinality values as fields, not tags. For example, store user ID as a field value rather than a tag. This prevents an explosion of index size. Second, create structured tag hierarchies. Group related dimensions like region, data center, rack. This lets you query higher levels first, then filter down, reducing query scope progressively. Third, use time bucket aggregation. Pre-aggregate your data by time windows for frequently accessed data. For example, create 1-minute rollups for dashboard queries to dramatically reduce volume while preserving the pattern you still have. Fourth, write shard-aware queries that limit time ranges to target specific shards. Use time now instead of unbounded queries to avoid scanning unnecessary data blocks. And this one got me almost every time I did a project. So now I always start with very small minimal queries, and then I expand from there to really see how long that reading takes. This directly addresses our first takeaway about handling that cardinality at a massive scale. Now let's travel to 2015. And that's the future in the Back to the Future trilogy, where we look at prediction. One of the most valuable aspects of time series data is its ability to help us predict the future without requiring a PhD in data science or having an AI model. Of course, you should use it as it gets better, but this is where it all starts. The key in using patterns detected in historical data is to make informed predictions. So the simple forecasting can be done with moving averages or linear regression. In our dashboard, we'll be able to project fuel consumption rates by calculating the average decrease in plutonium levels over time, then extrapolating to predict when we'll reach that critical threshold. Second, Grafana themselves actually includes built-in functions like trend and predict linear. Power BI has something similar that can visualize future values based on recent data points, so you don't even have to build that. And an Influx and other time series databases also provide moving average calculations that smooth out data and reveal directional trends pretty easy. For predictive maintenance, we can correlate engine temperature and power level patterns, for example. When we see a specific combination that's trending upward, we can predict potential issues before they cause those breakdowns. And resource planning becomes pretty simple when we understand consumption rates. By analyzing how quickly Mr. Fusion depletes plutonium during different types of time travel, we can predict exactly how much fuel we'll need for future trips. Finally, anomaly detection, which is arguably one of the most valuable parts of time series data, establishes a baseline pattern of normal operation. And it allows us to identify unusual patterns early, or even if we don't do it, that's something that can be handed to an AI agent that they also monitor. For instance, if the time circuit's voltage starts fluctuating in an unusual pattern, that you can predict potential failures before they occur as early as possible. The beauty of these techniques is that they don't require machine learning expertise. Just understanding time series data patterns and using the built-in functions of some of these tools are good enough to get started. With good historical data, even simple methods can provide really powerful predictions. But I want to stop right here and mention something. If you don't collect the data, it doesn't matter if you go and try to predict with it, because you don't have the data. So one of the most important decisions you will make, even if you are not the data scientist on the team, is how often, how much. You have to make that decision as a dev much earlier in the process than you think. And when in doubt, try to go for more granularity. You can always downsample in batches later. What I found, though, is that sometimes compression is the best way to do it. Get all that granular data and then shove it in a zip file and then put it in cold storage. At least that way you can unzip it and be able to look at it again. You have no idea what trend analysis you're going to need in like 5 years. So keep that in mind as you go. And this just gives you kind of an overview of what you can do as a developer as to why you need to collect what. Now it's time to pull everything together with our DeLorean dashboard demo. Okay, I've created a monitoring system for our time machine that demonstrates all 3 of our key takeaways. For the past, we're analyzing velocity patterns and time circuits voltage stability over time, showing how historical analysis can reveal patterns and trends. For the present, we're monitoring flux capacitor power and engine temperature in near real time, demonstrating efficient data writing and reading. For the future, we're predicting time travel events at 88 miles per hour and managing Mr. Fusion level reserves, showing how time series data using our stack can be done. Okay. Here's the architectural flow of our DeLorean monitoring system. It looks like every other architectural flow of anything you've ever built. There's just some input, you put it in a time series database, and you pick a visualization platform of your choice to look at it, right? But today we're going to use this. You can use anything you'd like, but this is what I'm doing. So that's really the takeaway here, is that it is not special to .NET in Flux or Grafana. It really is just about that input into a TSV and your visualization. So the way that this works, well, move it there. So our data is sent to Influx using the line protocol format that we discussed earlier, optimized for efficient writing. And then Grafana then pulls this data, uses SQL queries, and presents it in our interactive dashboard. The architecture demonstrates just 3 layers of those takeaways about handling high cardinality with an optimized data model and using an efficient write option and SQL for reads. That way it can scale from millions of data points with consistent performance and, of course, RAM power on whatever server it's on. The beauty of this setup is its simplicity, and this architecture works whether you're monitoring 1 DeLorean or an entire fleet. We're going to do 5 today. Yay! That's my favorite slide of the deck. Okay. So what I'm going to do is move my mouse over here. Yep. I'm just going to show you one that should be running theoretically right now. Yay. Should be. This is the last 3 hours. I can also change the last 15 minutes, the last 5 minutes. I actually like doing the last one. It's more fun. This is the fastest refresh rate that Grafana will give me. I understand that there is a trick to it to get it to less than a second. But really what you need is probably a purpose-built visualization just for real time. And there is a whole bunch of them out there. This was just the fastest, most satisfying way to get everything up on the screen for you all. And this is just being pulled directly in from my Grafana dashboard and showing it publicly to you all. All right. Okay, so the first thing that, I'm going to move this over here. Okay, let's look at the data generator behind our dashboard, yeah? Now that could be coming from anywhere or anything. I really wanted to show you all a lot of data coming in from Microsoft Flight Simulator, but I feel like that would overwhelm my laptop here. All right. Okay, so while this is already built, I want to just kind of go through it for you. It's actually running right now. You can kind of see at the bottom about how fast it's going. All right, so let's go up to the top. Yeah. All right, so we just got some parameters for each of our different levels that we're going to end up reporting into Grafana. It uses a background service that continuously generates and sends time series data to Influx, okay? Notice how we set up the connection parameters down at the bottom here. Using your URL, token, nobody take pictures, your org ID, and your bucket name. This is basically the same as like a database name. And Influx, it's called something different. With ClickHouse, it's called something different in Mongo. You can look up the correlation there. But these are the 4 things that you would need to change for you. I've already uploaded this to my GitHub repo, so you can play with it and pull it down. Yep.
With or without your token?
It's without. I made sure. You can check. You can check. I made sure it didn't have that in there. Absolutely. All right. So let's look at the simulated data parameters here. Where's my current velocity? It's up at the top, right? Yeah. Yeah. This is just the simulated data that could be coming in from a sensor. Obviously, it would if you have a Formula One race car, right? It would send it directly to you. But we're just going to simulate this for now. In a real-world application, these would be actual application metrics. Each of these represents a distinct time series that we will track over time. Okay, and then if we go over here, these right here, this is where cardinality comes into play. So we're defining several dimensions that could combine to create high cardinality. With 5 DeLorean IDs, 5 locations, 4 time periods, and 5 drivers, we could generate up to 500 unique combinations. Okay? This demonstrates how quickly cardinality can explode with multiple tag dimensions. Imagine if you were tracking a bunch of people on your Apple Watch, Fitbit, Garmin for the Boston Marathon, or maybe there's probably a marathon in Melbourne too. But imagine you have, admittedly, hundreds, and it just scales up from there. You might want to know where each one of them are at any given time, what their heart rate is, because you need to station nurses along the way in case somebody is getting a little bit too lightheaded, and you want to manage that in real time. This is where it starts to grow. All right, let's go to the execution loop here. You guys can see this all right, yeah? It's killing me to not have it in like dark mode, but it's okay. All right. Execution loop. Where did it go? Yeah, there we go. There we go. This is our main execution loop that runs every 5 seconds. For time series data, the collection interval is really important. So too frequent and you can overwhelm your storage. Too infrequent and you might miss important patterns. I definitely left this up overnight, and I can tell you I had to blow away my database and start again this morning. For the DeLorean metrics, 5-second intervals will provide a good enough balance, and also Grafana only refreshes up to every 5 seconds, so that's what we've decided to do here. All right, let's see, generate. All right, this is one of the most important parts of our code that we've got here. This is creating the line protocol format that we discussed earlier. Each line follows the pattern measurement tag key equals tag value, field, and I can't even say this because it's sideways. Measurement tag underscore key equals tag underscore value, field underscore key equals field underscore value, and timestamp. That's the pattern, okay? Notice how we're structuring our data with a consistent measurement name, DeLorean underscore stats, and using device as a tag key to differentiate the metrics. This is a best practice that makes querying a lot more efficient because we can filter by the tag, and you'll see that pointed out to you in the Grafana dashboard. The timestamp at the end is in nanoseconds, since Unix, the Unix epoch, which is, oh geez, it just left me. Yay. Since the Unix epoch, which is InfluxDB's highest precision, I thought it'd be fun to do it. I see what's happening here. I don't think that this likes me. You try it again? I have no idea what it's going to do when I do this, though.
You've travelled in time to a period outside of when this works.
Do you have a VGA connector?
I got it. It's just very temperamental. It's like 3 connectors together. All right. All right, everybody with me? Yep, okay. Very cool. All right. Where is my mouse? There we go. It's interesting to do this on a different screen. Okay. So here's our high cardinality right here we've got going on. Okay. This is where we deliberately create high cardinality data. For each generation cycle, we create 20 data points. And with randomly selected combinations of DeLorean ID, location, time period, and driver as the tags. This results in many, many unique combinations, exactly the kind of high cardinality challenge we discussed earlier. You should see the amount of data that comes again from Formula One. Notice that we're using a separate measurement name, DeLorean_detailed, to isolate the high cardinality data from the primary metrics that we're usually looking at. Also look at how we're slightly offsetting each timestamp by adding milliseconds. This creates a more realistic pattern of data points arriving with small time differences, which does happen with sensors, let me tell you. One sensor decides I'm going to be very fast, the other one decides it's not going to be. It's not all exactly at the same moment. This is a constant source of frustration for game developers when they're trying to manage multiple users at the same time getting to a particular part of a battle or a level in a map. You're having to decide when are they there, and ultimately everybody threw their hands up and says whatever the server machine says they did. But it might be more important if you're trying to guide something like a drone through the air. You need to know where that one is in relation to the other, and if their signals are one is weaker than the other, you're going to have to deal with some of those latencies. All right, got that there. All right. Here's our batch writing implementation that I mentioned. Instead of sending each line separately, although it is tempting, we join them with new lines and send them as a single HTTP request. This batch approach significantly reduces your network overhead and is really important for high throughput time series data collection. All right, let's send that to influx up there. Where did it go? There it is. Finally, here's how we send the data to Influx using the HTTP API. There's a couple of different ways you can do it. There is an SDK that could be in the programming language of your choice that you can do directly on the device, and you can host this locally. I'm just using the cloud version because it's easier for me, but if it's going to be that important, you're not going to want the latency of a cloud-hosted database for something, again, like a satellite guidance, or maybe not even if you're tracking stock trades. You might want that in your own data center and not have to deal with egress. Notice a few important details in this. We're specifying NS, which is nanosecond precision, in the URL. The authentication is handled with a token that is generated already for us inside of InfluxDB Cloud. You don't have to specialize a bunch around that, but you do have to put together the authorization header. The content type is text plain for line protocol data, and we have error handling to catch any failures. So this ensures our series data reliably makes it into Influx data, even at very high volumes, which was fun for me to figure out. All right, so that's all of our code here that we've got. And then let's take a look at the Grafana dashboard. I actually have JSON in here so that you can just copy it and then upload it to Grafana. I'll show you that soon, so you don't have to think about how to make it pretty or hire yourself a CSS person. And inside of it, we'll already have some optimized SQL queries for you. You don't have to use SQL, but it's nice because most of us know it. And that's for each one of the panels that you saw on that dashboard. Okay. So the gauge that shows the current power level of the flux capacitor is important. So let me pull that in. Where did it go? I think that's the first one I saw, right? I don't know. That's okay. We can go over to Grafana and look at it ourselves. All right. There we go. That's probably more meaningful because you can actually look at it. Okay, so the query for that demonstrates several best practices for time series SQL. It's select time and power level from DeLorean underscore stats, where device equals flux capacitor and time is less than or greater to now at an interval of 15 minutes. So that's what that one is set to. And again, you can see that directly inside of the JSON that I stuck in the project. We're selecting only the specific fields that we need, the time, the power level. We're filtering by the device tag to target only flux capacitor data. And most importantly, we're using a time filter to limit the query to the last 15 minutes. So even if I go over here to the dashboard itself and I change, that is just the cache that Grafana has. It's technically what you've put in there, it'll stay. And if I go to my Grafana cloud, I have a connection set up here already to my Influx Cloud instance, which I can certainly show you, but it'll take 2 seconds. Here, this is the URL to where it all lives. Here's the database name, and because we put in a token, the token actually already understands who we are. So that's all that we need for here. And then in the dashboard section, I'll show you the one I've got running right now. Maybe. Yeah. Cool. So now this is the edit mode, of course, of what you'd seen. If I go into here and scroll down, you can see that this is where you can mess with any of your queries. You can put it there. Again, this will work the same for Power BI or multiple different ones. But this is where you would really spend your time. So you see that that's basically hard-coded into this panel. So no matter what somebody does up here, they can't override what you've put there, but they can definitely filter it smaller if they need to. All right, let's go to the velocity chart. Let's see. Yeah, I like this one. It's pretty. All right. This time series chart shows our velocity over time with the critical 88 miles per hour threshold marked. And the SQL query is down below. It's select time and velocity from stats where device equals speedometer and time is less than or equal to now at an interval of 15 minutes. You're noticing a pattern. The right time of filter is honestly probably that for something that is in the most recent past. I haven't seen a lot that needed it more recently, although I know some meteorologists that would disagree with me. We typically only need recent data. There's a different one for each one of these dashboards. It's pretty fun to mess around with. Yeah, I think that's pretty cool. And the way that you get that started is pretty simple. So if oh my gosh. Okay. If I wanted to create, I don't need to do anything. If I wanted to create, it's haunted. Oh no, I'm giving up all the secrets, sorry. Maybe? There we go. Yeah, it's very gentle.
It's very temperamental.
I've got to be careful with it. All right, very cool. Yeah. All right, I think we got there. We did the Grafana stuff, which is great. Let me put that in here. Cool. You with me? Okay, cool. All right, if you wanted to add something, though, it's pretty easy. In this, you would just create a new importation of a dashboard. If you, again, don't want to build it yourself, you feel free to use mine, which is, of course, in here. It's interesting to move that. Okay. Yep. You just put it in, and again, at least that saves you some time typing all those queries in. All right, you load it up, like, oh, so that name already exists. Oh, no. Right. And then it'll allow you to pick which data source you want. You might have multiple databases. I find that I often do, and this is where you'll pick that up. You'll import it, and it should, theoretically, as long as that data has been coming in recently, which that .NET Console app is still running, we'll pick it up right away and let you go from there. So it's pretty fast way to start playing around with some of this data. Obviously, I can take you in a little bit of walk through what it might mean to do this inside of the Influx Cloud, but I will say this, you don't have to do that at all. You can set this up locally. And in fact, again, if you're somebody who's really into aerospace, I would suggest it. But this is probably good enough for weather data, right? And you would just go to manage your buckets. You see I've added a bucket there. You just create your bucket and give it a name. I can just say, there we go. Right. And then set it to a retention policy. I'm pretty good about setting it to 7 days and then leaving it alone. Or 72 hours also works. Then creating that. And then once you've done that, that's pretty much all that you need. You just need that name. And then you need to go to your API tokens and create one. You can generate one for queries that are for reads separate from any of that. But if you want one that can do both as your all access token, which is, of course, what we like to do. And then you just copy that over and you've got it. And if you want to know what your org ID is, you just go to settings and it should list that right there and your cluster URL. So that's pretty much it. You can also interchangeably use your organization name as well. Cool. All right. You get to see me drag it over. Nice. All right. Okay, so now that we've seen our dashboard, right, let's take a look at how time series data predicts the future a little bit more, shall we? Do it. That's fun. Does not want to do it. Let me try this. Okay. That's fun. I guess I could manually try to do it. Come back. Okay, there we go. We've got it, dude. Appreciate you. Okay. Our predictive maintenance query uses the derivative function to calculate how quickly engine temperature is rising. If it exceeds 2 degrees per 30 minutes, we can predict overheating before it happens and alert maintenance that it's needed. The plutonium consumption forecast does something even more practical. It predicts when you'll run out of fuel. I wish my car had this more than just a light that comes on. It gets our current plutonium level, calculates our hourly consumption rate, and divides level by rate to determine hours until empty. And no machine learning is required for this, right? It's just simple time series functions you've all probably done in different ways. But this demonstrates that it really isn't just about like past or present. It is about using those patterns to predict in the future as well. If you are interested in what I built today, this is the GitHub repo for that. It's all available on GitHub, and I included a full build from scratch instead of just fork it and go, if you're interested in all of the steps there. The repo includes the complete .NET generator, the Grafana dashboard, SQL queries for all the panels, and set of instructions. And feel free to modify it and add more fun things. I'm going to build this out even more as I go for the next few months. So no matter what you're monitoring or trying to look at least getting your head in this space this way is really helpful as a beginning. And a lot of the folks I know have started pivoting to data science because they started as a dev messing with time series data. So as we wrap up our journey here, we're just going to make sure that we've covered everything, and you'll have to keep me honest on that. We covered strategic tag selection, right? Structured hierarchies and time bucket aggregation. Yes? Okay. These approaches ensure that your database remains performance. Second, we've explored how to write data really efficiently, really fast with line protocol and read it with SQL, but also create good SQL queries that make sense for what you're doing, which means you just can't copy paste. This is the hardest thing right now I found, is explaining to an LLM that I want to change what it has trained on, and I want to do it specific and bespoke for my industry. Third, we've demonstrated how to scale from thousands to millions of data points without performance loss. We went over downsampling, compression, cold storage, and multi-tier architecture. Yes? Cool. All right. Then I think that's everything I have to give you. I appreciate you doing this with me today, and have a great conference.